Least fun for everybody. So try to avoid using that word. Okay, so here we go. So chapter 2, practice. Tamiflu is an effective antiviral used to treat the flu. Has the following structure: identify the functional groups in Tamiflu. So since this is our first one, why don't I circle some of these and you guys try to help me out? So if I identify, or if I circle this one, could anybody tell me which functional group I'm dealing with here, the one circled in green? Yeah, absolutely. So this one is an ester. Thanks. Ester. That's right. Are there any other functional groups that you guys recognized in there? Let's see, there's 4 more in there. Yeah, absolutely. There's an alkene. Thanks, Rubio. Yep, there's an alkene here. So we'll circle that. We'll put alkene. What were the other ones? An amide. Yes, absolutely. Right. There's a beautiful amide right here. Yeah, that would be an amide. So amide. There's 2 others. Anybody identify the other ones? Yeah, thanks. There's an amine. Yes. So this is an amine. And then the last one is this one here. We have carbon, oxygen, carbon. And so that is an ether. I'll put this one way over here, is an ether. All right, so we have a total of 5 functional groups in that one. The next one is aspartame, which is an artificial sweetener. So aspartame is actually made out of 2 naturally occurring amino acids, so aspartic acid and phenylalanine. That's neither here nor there. But let's see if we can identify some functional groups in aspartame. Is there anyone that anybody recognizes in aspartame? Aromatic, heck yeah. Yeah, beautiful aromatic right here, isn't there? Yeah, so we'll circle that and we'll put aromatic. Aromatic. An ester, yeah, there's an ester in here. So this is an ester, sure. Oops, Mr. Dion. There we go. Any others? Don't be shy. Somebody says a ketone. So there's no ketone in this one. There's a carboxylic acid though, yep. So a carbonyl that has a hydroxyl attached to it directly. That's a carboxylic acid. So carboxylic acid, yep. Any other ones? So this carbonyl, right? You always have to take the 30,000-foot view. So that carbonyl has a nitrogen next to it. So if we circle that entire thing, okay, that would be an amide. An amide. There you go. And somebody said an amine. Yep, there's an amine right here. So we'll put that over here. There is an amine. There we go. So there's what? A total of 5 functional groups in aspartame. All right, great. So there you go. We covered those 2. Let's move on. So the next one says, let's identify some resonance forms for this compound. I'm going to redraw the compound down here just so I have enough Taylor Swift blank space to put it. So remember, there's a carbon atom right here where this black circle is, right? That's an sp hybridized carbon. So put this. And we have a negative charge here. Okay, so can anybody tell me where the lone pairs are missing from this structure? Where are the lone pairs missing? On the nitrogen, yeah, there's a lone pair on the nitrogen, and then there's one more. On the carbon, right, exactly. If we have a carbanion, there must be a lone pair on it. Maybe I could put it, there you go, something like that. So the first pattern that we recognize is we have an allylic lone pair. Great. So we can draw 2 curved arrows to draw the resonance form of that allylic lone pair. So we're going to form the double bond. Lost everything. Okay, let's start over. So we'll form the double bond. So where was I? Something like this. There we go. So somebody said lone pair here. There we go. Okay, so let's get started. So we're going to start with our allylic lone pair. So move the negative charge over here. And so let's draw what we get from that. So now we've got a double bond here. We've got our carbanion here. And then we've got a triple bond down here like that. So that's a resonance form. Now, keep in mind that we can have resonance as long as we have a pi bond. A triple bond has 2 pi bonds in it. And so we have another allylic lone pair here, okay? Even though this carbon is linear in its molecular geometry, it doesn't change anything, we can still draw another resonance form for it. So we're going to draw a double bond here, and then we're going to move a pair of electrons down onto the nitrogen. So now what we end up with is we have our original double bond. We have this carbon, which now has a double bond. And then we have the carbon here. I'm going to put a little dot to represent this carbon here. And then we have another double bond. And now our nitrogen has a double bond and 2 lone pairs. And so it's going to have a negative charge, right? Charge of -1. When nitrogen has 2 bonds and 2 lone pairs, it has a formal charge of -1. And so these would be all of the resonance contributors. So what's the only pattern that we used in here was allylic lone pairs. Okay, that's the only one that we used to draw these 2 resonance forms, was the allylic lone pair. Now keep in mind that this carbon here, the one I represented with the little black dot, right, it's got a steric number of 2, and so the bond angle here must be 180 degrees, and that's why I drew it linear like that. So there you go. So those are the 3 resonance forms for this guy. Let's try the next one. We have a positive charge on a nitrogen. We've got a negative charge on an oxygen. Let's see if we can come up with some resonance forms here. So I'm going to redraw the first compound. So I'll just redraw it down here. So we've got our lone pair here, lone pair here. All right. There we go. Open bracket. And so where are we going to start? Well, the first one that I notice is that you have a lone pair next to an atom with a positive charge, right? This nitrogen has a positive charge, and we have a lone pair here. So I'm going to dump this lone pair in here like that to give that nitrogen an octet. So when we do that, let's draw what we have. Now we have a triple bond between our nitrogens. This one still has the lone pair. We have our single bond out here. We have our negative charge here. So could anybody tell me where the positive charge is now? Is it on the charge, the nitrogen on the left, or the one in the middle? Is it the left one or the center one? Yeah, it's on the center one, right? When nitrogen has 4 bonds and no lone pairs, it has a charge of +1. All right, great. So there we go. So this one was the lone pair next to positive charge. And then we have another one here that we can draw. So we have another allylic lone pair here, right? We have pi bonds and we have a lone pair here. So we could draw another resonance form where we put the electrons over here. So we end up with something that looks like this. So now we have a double bond here. Nitrogen has 2 bonds and 2 lone pairs. This nitrogen has 4 bonds, and the oxygen looks like this. Okay, so now where are my charges? Could anybody tell me where the negative charge went? Let me just fix this nitrogen here. Where's the negative charge? Remember, when nitrogen has 2 bonds and 2 lone pairs, it has a charge of -1. So our -1 charge is here, and our +1 charge is here. So we have allylic lone pair is the one that we drew here. All right. So sometimes students will ask me, here I have a lone pair between atoms. One has a positive charge. Why can't I dump these in here? Why would that be a bad arrow if I was to just draw that? Just that blue arrow by itself. Well, if I was to draw it, and don't draw this because it's wrong, but you'd end up with something that looks like this. What's the problem there? Is that you've broken the octet rule. Exactly. Thanks, Rubio. Yep. So you break the octet rule. So that would not be a legitimate resonance form. There you go. All right. So we drew some resonance forms there. The next one, draw significant resonance structures for the following compound. Which of these are most significant? So we didn't answer that with this one. But if we take a look at number 1, so I'll call this one, I'll use my green pen. I'll call this number 1, number 2, and number 3. Out of those three resonance forms, can anybody tell me which one is going to contribute the most to the resonance hybrid? It's not an easy question, but it does follow the rules we went over. Okay, it's not going to be number one. And the reason why is because in number one, right, exactly, because in number one, the nitrogen is electron deficient, right? It doesn't, this nitrogen does not have a complete octet. So this one is actually going to contribute the least. The reason that number two is going to contribute the most is because everybody has an octet. In number three, everybody's got an octet as well. But what's the difference between 2 and 3? In 2, the negative charge is on the more electronegative element. So this one is going to contribute the most. So number 2 will contribute the most. 3 is somewhere in the middle. And then number 1 is going to contribute the least. So now let's do the same thing with this guy here. Does anybody notice any of the patterns here? Any of the patterns that you recognize for this one? For this compound, does anybody recognize any of the patterns that we took a look at? I see 2 of them that are, yeah, we have an allylic lone pair. Let's go with that one. We have an allylic, come on you. Of an allylic lone pair right there, exactly. So what Isaac is saying is he says, well, you got an allylic lone pair. So let's form a pi bond. Maybe not my best arrow. Let's form a pi bond and let's break this like this. Okay. What you're going to see is that's actually going to cause a problem if I draw it that way, because then you'd have a negative charge on this carbon next to a positive charge here. Those 2 atoms are both carbons, so we're not going to have one with a positive charge, one with a negative charge. So what we're going to do instead is we're going to form a second pi bond over here. Okay, so what that's going to look like is this. We draw our resonance form like this. Now we've only got one lone pair on here. We've got a pi bond here. We've got a pi bond here. And then we have our pi bond out here like this. So now we have a positive charge on our oxygen. Okay, so that's a legitimate resonance structure. Are there any others? Well, the answer is yeah, absolutely. Okay, here we have a positive charge between atoms of differing electronegativity. So we could draw a resonance form there where we could break this bond and put the lone pair over here. Sorry, put the lone pair over here on the oxygen. And that would give us, I need a finer tipped pen here, I think. But anyhow, that would give us something that looks like this, where we have a carbocation here. Yeah, I need to put this down here. I'm running out of space. So I'll move this down here, okay? So I'll fix this after. Anyhow, so we'd end up with something that looks like that, and then we still have this double bond, this single bond, and this double bond. Like this. Okay, so that's our next resonance form. And then you see we have an allylic carbocation, right? We have an allylic carbocation right here. And so we can draw a curved arrow for that. That's going to take us right back to where we started. If I draw this curved arrow here, that's going to bring us back to the original compound. So I'll just prove that here. So we have 2 lone pairs here. We have a double bond here. Now our carbocation is going to be here. Son of a gun. Keep running out of space. There we go. And so we have this one here like this. So there's one more resonance form we can draw. I'm kind of running out of space, but it's going to be the allylic carbocation, right? We have an allylic carbocation, so we can draw one more resonance form, which is going to look something like this. I'm going to have to draw it in a weird space here because I'm running out of space, but it's going to look like this and this, and there you go. And now the positive charge is going to be out there. All right. Whew. Okay, so we've gotten through all of them. If I call this one number 1, I'll call this one number 1, 2, 3, and 4, because remember, this one is the same one as number 1. But if I look at all 4 of those, could anybody tell me which one of those is going to contribute the most? Which one is going to be the most significant resonance structure? It's not going to be number 4, because number 4, the carbon has an incomplete octet. right? There's one of these structures where everything has a complete octet. It's number 2, isn't it? Right? Number 2 is going to contribute the most. And we'll put here because complete octets. Everything has a complete octet. Exactly. All right. So with that in mind, let's try the next one. So the next one's about caffeine. Maybe you could use some more. I think I could. Actually, it sounds like a really good idea. Okay, caffeine has the following structure. What is the hybridization state and molecular geometry at each nitrogen? So there's 4 nitrogens. First thing we'll do is we will put in all the lone pairs. So there's a bunch of lone pairs missing. There's 2 on the oxygen that are missing. There's 2 on this oxygen that are missing. There's 1 lone pair on each nitrogen that is missing. So I'll highlight this nitrogen in yellow, this one in red, this one in blue, and this one in green. And what we'll do is we'll try to determine the hybridization state and molecular geometry at each one of them. Let's start with the nitrogen in yellow, okay? So I'm going to ask you guys, can the lone pair on the oxygen in yellow participate in resonance? Just yes or no. I don't need to know where it is, but can it participate in resonance? Is it allelic to a pi bond? Yes, it absolutely can. Can it, Isaac, right? I'm not going to draw the resonance form, but you could draw this as a resonance form, right? That lone pair can participate in resonance. Okay, so if it's participating in resonance, what was the rule? What's the hybridization of that nitrogen then? And it's not a trick. I'm not trying to fool you or get you or something. If it can participate in resonance, what's the hybridization of the nitrogen? What was the rule? We go back to 2.12. It's sp2. Exactly. Yes. Now, if the nitrogen is sp2, its molecular geometry must be trigonal planar. Okay. It's flat as a pancake. All right. Same. Well, no, I shouldn't say that. I should be careful what I say. I'm trying to teach here. What about the lone pair on the nitrogen in red? Can that participate in resonance? Again, there's no trick questions. There's nothing trying to fool you or tease you. Can that lone pair in red on the red nitrogen, can it participate in resonance? Absolutely. Thanks, Rubio. Absolutely, right? You could draw a beautiful resonance structure like that. Nothing wrong with that, right? So again, if that lone pair can participate in resonance, it looks like the nitrogen has a hybridization of sp3, doesn't it? But we know it's not. It's sp2 because in order for the lone pair to participate in resonance, it has to be in a p orbital, right? So we know that the nitrogen is actually sp2. And again, its molecular geometry must be trigonal planar. All right. This is really crucial for my students who are going to go on to biochemistry, because when you look at peptides and proteins and enzymes are held together by amide bonds. And so this, essentially is an amide here. And so the fact that the nitrogen in a peptide bond is sp2 hybridized, it's trigonal planar, has some very pertinent consequences to the structures of peptides and proteins. Okay, let's try the one in green. Okay, the one in green, a little trickier. Now that nitrogen has a double bond on it, and it also has a lone pair. So can that lone pair participate in resonance? No, exactly. It can't, because it's in an sp2 hybridized orbital, isn't it? Okay, so the nitrogen is sp2. The lone pair is in an sp2 hybridized orbital, but it can't participate in resonance, okay? Because in order to participate in resonance, you have to be in a p orbital. So what's it asking for here? It says, what's the hybridization state of each nitrogen, and what's its molecular geometry? So this one is also sp2, okay? And it's trigonal, son of a shit. Trigonal planar. But I think what I'm neglecting to do here is write whether they're localized or delocalized. For the 2 in red, we're going to write both of these. So we'll say this one and this one, delocalized, right? Because those lone pairs can participate in resonance. The one in blue cannot participate in resonance. Sorry, the one in green cannot participate in resonance. So we'll put here localized. And then what about the last one? That lone pair in blue. I'll use my black pen this time. Can that lone pair participate in resonance? Yes or no? Heck yeah, I can. Right. Thanks, Hannah. Yeah, absolutely. You could, it's a right. It's allylic to a pi bond. Yeah. So there you go. You could draw a Lewis or a resonance structure for this. So that means that that nitrogen is also sp2 hybridized. Where'd my black pen go? It's sp2 hybridized. The nitrogen is going to be trigonal. I'll just put trig planar, and the electrons are delocalized. There you go. So the only one that has a lone pair that's localized is the green one. So let me try that again. So sp2 trig planar and delocalized. There you go. All right. Cool. Caffeine. Now you know the structure of caffeine. You probably knew it before, but now you get to look at it again. All right. Let's see if we can draw all the resonance forms for phenol. So this is phenol, and we're missing some lone pairs. Where are the lone pairs missing on this guy? Anybody? Where are the lone pairs missing in phenol? On the oxygen, exactly. Yeah. There's two lone pairs missing on the oxygen, right? Remember water, when oxygen is neutral, it has two bonds and two lone pairs. Okay, so it's missing two lone pairs. There we go. So what do we notice first is that we have an allylic lone pair. So let's start with our first resonance form. So what I would like you to do is I'm going to give you a few seconds, and I want you to try to draw without me doing it first. I want you to try to draw the result of these two curved arrows. Okay, I'll give you a few seconds to try. Okay, so I'm going to start penciling it down here. So I like to start with the parts that I didn't change. So I didn't do anything to the ring. That's still intact. I didn't touch this. Oops. I didn't touch this double bond. I didn't touch this double bond. I made a double bond here. So now the oxygen has a lone pair on it, and I have a lone pair here. So where are my formal charges? I'm going to go a little faster now. So now my oxygen has 3 bonds and 1 lone pair. It's got a charge of +1. And my carbon has 3 bonds and 1 lone pair. It has a charge of -1. So now what we got to do is we have to draw 3 more resonance forms for phenol. So we're going to draw our resonance arrow, another 6-membered ring, and we see we have an allylic lone pair. So we're going to show the electrons being delocalized. So let's draw the result of that. And now we've got a single bond here, double bond here, double bond here. We have our positive charge here, and we have our carbanion down here. Now we have another allylic lone pair, right here. So now we can draw another set of curved arrows. There's my other electron. There it is. All right, so we're going to make a new pi bond, and we're going to break this one. And there we go. So we end up with something that looks like this. So there we go. And there you have it, friends. So those are all the resonance forms for phenol. Could you draw another one? Yes, you could do this. Okay, and it's going to take you right back to the beginning. Okay, you're going to have something that looks like this. Okay, it's not necessary to do that, but it's okay if you do it. Now, sometimes students will try to argue and they'll say, well, hold on, here the double bond starts here, and here it's a single bond. It doesn't matter where they are. Remember, these are delocalized. Okay, it's still the same molecule. It's still showing phenol. It doesn't matter where the bonds start, and as long as they alternate, it's the same structure. Cool? All right, give me a thumbs up. Everybody with me on that one? Any questions about the resonance forms of phenol? Okay, cool. All right, if you have a question, don't hesitate to stop me at any point. Okay, we have a couple more. Oh, I see some of these are from the textbook that I stuck on here. So the next one just says throw in some formal charges. So let's review the formal charges quickly, okay? The main ones you need to know Come on, you. Main ones? No, still not right. There we go. You need to know carbon, nitrogen, and oxygen. Okay, you need to know when it's -1, 0, and +1. Well, you guys know that when carbon has 4 bonds, it has a formal charge of 0. When carbon has 3 bonds, it has a charge of +1. And when carbon has 3 bonds, did I put it in the wrong spot? Son of a gun. There we go. When carbon has 3 bonds and no lone pairs, it has a charge of +1. But when carbon has 3 bonds and a lone pair, it has a charge of -1. Okay, for nitrogen, when nitrogen has 3 bonds and 1 lone pair, it has a charge of 0. When nitrogen has 4 bonds, it has a charge of +1. And when nitrogen has 2 bonds and 2 lone pairs, it has a charge of -1. For oxygen, when oxygen has 2 bonds and 2 lone pairs, it's 0. And it could be 2 single bonds, or it could be a single and a double, doesn't matter. Okay. When oxygen has 1 bond and son of a gun, can't see, and 3 lone pairs, it has a charge of -1. And when oxygen has 3 bonds and 1 lone pair, it has a charge of +1. You have to have this, I would say, memorized. Okay, can you calculate it using the formal charge rules every single time? Sure, you can. However, you want it to be pretty much a second nature because you have to identify them really quickly. So if you know those rules, you can look at the first one and say, this nitrogen has 2 bonds and 2 lone pairs. Therefore, it has a charge of -1. On the next one, the oxygen has 1 bond and 3 lone pairs. It's -1. The nitrogen has 4 bonds, so it's +1. On the next one, did anybody find any formal charges in this guy? In the one I have in the red circle? And again, there's no trick questions. I'm not trying to tease you or something, but are there any formal charges in this? No, there's none, right? So we'll just put here, none. What about the next one? Excuse me. Where would I find the formal charge in this one in the red circle? Oxygen is +1. Exactly. Thank you. So the oxygen is +1. That's right. And that's the only one. And then in the last one, the nitrogen is going to be +1 because it has 4 bonds. And then the oxygens, well, we're missing some lone pairs, but this oxygen has 2 lone pairs. This one only has 1 bond, so it has to have 3 lone pairs. And therefore, we have a -1 charge here and a +1 charge on the nitrogen. This one here has an amine in it and the conjugate base of an acid. This is actually an amino acid. Amino acid. It has a name. It's called alanine. Alanine, which you don't need to know for now. But anyhow, now you've seen it. So let's see. Let's do these ones a little bit more rapidly. But it says, I use resonance structures to help you identify all the sites of low electron density. So one of your goals as an organic chemist is to be able to look at a molecule like this one and say, well, where might there be a site of reactivity? Okay. How is this molecule going to react? You know, this is what organic chemists
do. We don't have that last page on the practice.
You don't?
No.
Okay. I'll find it for you. Just give me a second. Okay, you can actually, I'll tell you what, why don't you just write it down? Okay, just grab a pencil and a piece of paper and scribble it down. Okay, there you go. Just take a pencil and a piece of paper, 6-membered ring, and just draw it. Okay, this is just question 2.60. But as I was saying, you know, a chemist has to be able to look at this structure and say, well, how might it react? Okay, so I'll redraw it myself. So if we draw the compound, so, and again, you have the solutions to this one because it comes from the textbook. There you go, done. Okay, so if I draw this compound, we see the oxygen is missing 2 lone pairs. So could anybody tell me where we might start with this? Does anybody see one of the patterns in here. We have the aromatic, that's one, but I wouldn't start there. Does anybody see any of the patterns here? If I was to circle this part of the molecule, okay, what pattern would I use here? Okay, I have a double bond between two atoms of differing electronegativity. So if I was going to start with a curved arrow on the double bond, okay, would I draw the electrons going up to the oxygen, or would I draw them going down to the carbon? Could anybody tell me? Which way should the curved arrow go? So which atom is more electronegative? Is it oxygen or carbon? Exactly. Oxygen is more electronegative. So if you have a double bond between atoms of differing electronegativity, the more electronegative element is going to take the electron. So now, when we draw the resonance form of this guy, it's going to look like this. So we've got our aromatic ring. Okay. Double bond. Now we've got a single bond here. Now we have a carbocation here, and we have a negative charge on our oxygen. So now you can see that you have an allylic carbocation. This is the first resonance form that we looked at, right? So now we can draw a resonance form for it. So we can put these electrons over here to stabilize the carbocation. And what are we going to get in return? So now what I'm going to do to make things easier, for the aromatic ring, I'm just going to write pH. So pH represents an aromatic ring that has a bond attached to it, okay? So I'll put pH, double bond. Now I've got a single bond here, and I've got a double bond here. And so now I've got the negative charge on my oxygen and the positive charge here. So now I see another pattern, right? I have another allylic carbocation. So I can draw another curved arrow like this and draw the next resonance form, which is going to look like this. And now I have the positive charge here. Now, in order for me to draw the next resonance form, I'm actually going to have to draw out the whole aromatic ring, right? I've got to draw the whole aromatic ring. And I'm not going to do it right now, okay? I want you guys to try this without me showing you, because can you learn some things by watching somebody do it? Sure, but you can't learn to ride a bicycle or play the guitar by watching somebody. You have to try it yourself. So you'd say, I've got another allylic carbocation here, so I'd push another arrow like this, and I'd keep moving forward. But what you can see is that we have a delta positive on this carbon, and then we have a delta positive on this one and this one. And what you're going to see is, if you draw your resonance forms correctly, is that the delta plus is going to alternate all over the entire molecule. So all of these atoms that I have it written by, when you finish all the resonance structures, and there's three more, right? You'll have to draw a resonance form with this one, with a carbocation at those three carbons. You'll see where the positive charge is delocalized throughout the molecule. So a good organic chemist here, he should be able to look at a molecule and kind of assess this in their mind's eye. Where are the sites of electropositivity? Because if I put it in the presence of an anion, maybe it will react at one of those centers. All right. And then for the next one, again, if you don't have it, just write it down. Okay, I'll write it down with you. So just get a piece of paper, just scribble it down. Aromatic ring, 3 double bonds, hydroxyl here. And then we have something that looks like that. There we go. So how would I start with this one here? Well, again, you could start with the bonds in the aromatic ring, but that won't really give you anything too interesting, because it doesn't show you where there's high electron density or anything like that. But you do notice that if we put in the electrons on the oxygen, that we have an allylic lone pair. So for that, we need 2 curved arrows. And so if we draw the result of those 2 curved arrows, what are we going to end up with? It's going to be something that will look like this. So I have my single bond here, or sorry, my double bond here, double bond here. Come on, iPad. There we go. All right, so we have something that looks like this. This. Here we go. So now I've created a double bond here. Okay. I have my hydrogen here, and now I've got a positive charge here, and I've got a negative charge here. So now what we're going to do is we're going to keep drawing more resonance forms. So you have an allylic lone pair here. So you're going to do the same thing. So you're going to make a double bond and you're going to delocalize these electrons down here. So what you'll see is that your delta minus is going to show up here. It's going to alternate down here, 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 and here. And you should be able to draw all 5 of those resonance forms that shows the negative charge being delocalized throughout the molecule.